Our next presenter is Don Sadoway, who is going to be talking about innovative energy sources. And what I learned in innovative energy, and what I learned in 3091 was all I needed to know. And I understand he's working on liquid batteries, and he's going to have one here that's a prototype, $1 million battery. And perhaps he'll have a better topic next time. Please join me in welcoming Professor Sadoway.
Actually, the battery consists of molten metal at elevated temperature, and I'll tell you all about it, and you will not want to be drinking from it. But all right, well, I have the enviable task of speaking to you before lunch, and I will try to do that in a painless way. So what I want to do is to talk about the whole business of going against the grain, thinking differently, and I want to give two examples. One comes from research, and so I will talk about grid-level energy storage, but I can't resist talking about teaching and about going against the grain in the classroom, because I think that stimulating our young minds in order to be able to invent is probably the most important thing that we do. So if you want to stimulate minds, you have to get started early, and so I like to do that in a freshman class, because as you know from parenting, the most important thing you can do to ensure a good finish is to get them off to a good start. And the freshman year is the start. So let's get started. So I'm going to talk about storage first of all. Storage is the key enabler. And so, for example, for deployment of renewables, it's critical that we address their intermittency. Well, what happens if the sun doesn't shine? Even if you had 100% conversion efficiency, solar would never make it to base load. So we have to address that intermittency. And in grid-level storage, we have to think about the problem differently, and that's what the theme of today's conversation is. When combustion is an option, you know what happens when the sun doesn't shine? They power up gas-fired combustors. So you have this green front, and in the back is hydrocarbon combustion. All right? Batteries invented for portable applications are not scalable at cost. So you cannot think about stringing together a bunch of lithium-ion batteries that were invented for cell phones and laptop computers. This is inverse synergy. The whole is less than the sum of its parts. Right? So a couple of general observations about batteries. Don't pay for attributes you don't need. So for example, the cell phone needs to be idiot-proof because by and large it's in the hands of idiots. All right? So the car needs to be crash-worthy. So when people tell you that all of the cost curve that we've chased down in cell phones is going to drive the price of electric vehicles forward, no, because the cell phone doesn't have to be crash-worthy. What about service temperature? Well, if it's going to be in contact with the human body, it has to be, obviously, near ambient temperature. The stationary batteries are not a consumer product. Only specialists are going to touch these things. So you have much more freedom and choice of chemistry, but here's the problem. Hydrocarbon combustion is your competition, so the price point is very low. How low is it? Well, you build a laptop, you're paying about $2,000 to $3,000 a kilowatt hour for the battery. That's the capital cost of the battery. Cell phones about $1,000 a kilowatt hour. The goal for automotive traction for all electrics is $100 to $200 a kilowatt hour. Now think about it. A 50 kilowatt hour pack at $200 a kilowatt hour, that's $10,000. For a battery that could poop out in 2 years the way your laptop does, that's the challenge. All right? But look what happens when we get to stationary, $50 a kilowatt hour. That's really, really low. And for those of you that argue that the market will just get the price right, there's the severity of service conditions, and here's the price. So if you start a battery company, you're going to sell batteries for toys. And here's where the societal need is. It's quiet in here, isn't it? All right, so how do we think about inventing in this space? We've got to think differently. So my other research in electrochemistry is in electrometallurgy. Yes, I was formerly educated as a metallurgist, how to turn dirt into metal. And I'm particularly interested in electrometallurgy, the use of electric current to produce metal, aluminum, magnesium, titanium, and so on. Look at the economy of scale of an aluminum smelter. We take bauxite from one corner of the globe, cryolite from a second corner of the globe, petroleum from a third corner of the globe, put them into a plant at an annual capital cost of $4,000 a ton, shoot 5, 6, 7 kilowatt hours a pound of electricity across the cell, and we can make virgin metal for less than 50 cents a pound. We make beer cans out of this stuff, for goodness sakes. Right? So, how do we take the economy of this and apply it to batteries? Well, first of all, we don't make aluminum in little beakers. Right? To make metal by the ton, we have a cell the size of the front of this stage, up to my knee in liquid aluminum, and a layer of about 2 or 3 inches of molten salt, and then some carbon anodes coming down, 500,000 amps, and we tap out aluminum by the ton. So why aren't we building batteries that way? Instead, we're putting a whole bunch of these little stupid tubes together. This is what a modern smelter looks like. It was invented in 1886 simultaneously in the United States and in France. Charles Martin Hall here and Paul Héroult in France. This is the patent from Charles Martin Hall. It was issued in 1889. Looks pretty much like a U.S. patent today. Are you ready to see what the French patent looked like? Monsieur Paul Louis Toussaint Héroult, there it is, procède électrolytique pour la préparation de l'aluminium. And it's very florid. Oh, the last page has got signatures. Yeah. All right, so how do we think against the grain? Well, pose the right question. Pose the right question. So the problem with batteries is one of the many problems, and certainly for this application, is that batteries intrinsically store charge, but they don't like high current. So everybody out there is trying to figure out how to teach a battery to handle high current. Well, I turned the problem around. I said, why don't I start with something that intrinsically loves high current and teach it how to store charge? What if I took this and turned it into this? How do I turn an aluminum smelter into a battery? Well, first I asked, why is an aluminum cell not a battery? Maybe the aluminum industry sitting on top of the solution didn't know it. Well, here's what the cross-section of an aluminum cell looks like. This is the electrolyte, the orange here. This is liquid aluminum. Current shoots across the electrolyte, make liquid aluminum at the bottom, and we make carbon dioxide gas at the top, and it's a fugitive emission. So it's not available for recombination. So I gave a little bit of thought to this and realized that even if I could trap the CO2, it wouldn't react on the return. I have to produce liquid metals at both electrodes. Liquid metals at both electrodes. Now, I hate to give you chemistry just before lunch, but here it goes. You know that every compound consists of a metal and a nonmetal. Right? So making metal is easy. That's how we make aluminum, magnesium, and so on, by depositing at the cathode through the action of electrolytic action. But I want in the same place at the same time to make one metal at the cathode and make a different metal at an electrode of opposite polarity. And that's impossible, because that's where the nonmetals go. Now, I'm going to tell you, anybody who's taken 3091 could solve this problem. You always go back to basics, periodic tables. So I'm sitting there looking at a periodic table. Here are the metals. There's magnesium, sodium, and there are the nonmetals over here, the chlorine, oxygen, and so on. So this goes to the cathode, this goes to the anode. And these don't conduct electricity. They're no good for this application. But what about this? You see the staircase here, that red staircase? I know you can't see that, so I blew it up for you. Here's the staircase. See? You see antimony? Antimony by itself is a metal. It's lustrous, it's ductile, it conducts electrons. But if you put antimony in the presence of I'm going to use an adverb here, a really good metal, like magnesium, magnesium, which is a really strong electron donor, intimidates antimony into being an electron acceptor. And antimony starts behaving as a nonmetal, even though it's an electron conductor. See, it's due to the difference in the electronegativities. This is very electropositive. These are mildly electronegative. It's just the difference in the electronegativity. It's a lecture in freshman chemistry. So, thanks to alums like you, Desh Deshpande and Arunas Chasonis, there is money on campus that allowed us to get started under the radar. And with that money, we were able to start the work and invent what I call reversible ambipolar electrolysis, which sounds academic, but in plain English, it's a liquid metal battery. And here's what the liquid metal battery looks like. You've got a metal on the top, metal on the bottom, and a molten salt in between. Two liquid metals. And on discharge, what happens, the magnesium, which is less dense than the electrolyte, dissolves to form magnesium ion and liberates electrons. And on the other side, antimony dissolves but consumes electrons. So I have an electron source, I have an electron sink, I connect this to a load in the external circuit, and I can generate current. And if I want to make a big one, instead of having a whole bunch of cells the size of soda cans, I could make a cell the size of this stage. Scalable. I think that's different. So here's some basic science just to show that we don't just play with liquid metals and blow bubbles and so on. So this is a current voltage characteristic. We're measuring the current as a function of potential. What happens with zinc chloride as a supporting electrolyte? If we go to very cathodic values, we see a peak here associated with zinc deposition. We start sweeping back. This is the stripping of the liquid zinc that has just been produced. Temperature here is 500 degrees C. Zinc melts at 420. And if we go to the other extreme, we get chlorine evolution. Now what I'm going to do is I'm going to dope this with zinc telluride. Why? Because tellurium is one of the elements on the staircase. I put a little bit of zinc telluride in here, and now I'm going to focus on this limited range of voltage, well below the anodic evolution peak of chlorine. And what do we find? Zinc deposition, zinc stripping, and a very modest potential, tellurium deposition, tellurium stripping. Now you say, well, he's got peaks. How do we know it's tellurium? So I'm going to park at this value of potential and drive current through the system. Here's some glassy carbon. This is 1 millimeter marker, so that's about 3 millimeters in diameter. That's a big blob of tellurium, and I know it's tellurium because I measured its X-ray diffraction pattern. So this is metal at the anode. You know, metal at the cathode is dog bites man. Metal at the anode is man bites dog. This is different. And here's what it looks like in the lab right now these days. There's the human scale. We put together these cells, cycle them, and so on. They go into a can right now. The baby ones need extra thermal nutrition, so they go into a furnace. At full scale, these things would be self-heating with cold sidewalls, just as an aluminum smelter is. So here it is in the furnace and battery testing and so on. We cycle test them and whatnot. So here's one of these things cut away. There's the blob of liquid metal that was the electropositive anode, that was the molten salt electrolyte. Here's the electronegative cathode. And you can see the metals have high surface tension, and you can see this thing wants to ball up because this is only a couple of centimeters in diameter. You make something several feet across, you'll have a little bit of a meniscus, and it'll be as flat as a pancake. That's how we make plate glass so flat, right? We pour the liquid silicate on a molten tin. So I know the meniscus isn't going to look like this over a span of tens of feet. Otherwise, the windows wouldn't look so good, would they? All right. So what are the attributes of this? Very low activation over voltage, so parasitic losses are low. No solid state diffusion, and that's what degrades your lithium-ion battery. We don't have any of that. And the all-liquid configuration is self-assembling. The low-density metal sits on top of the electrolyte, which sits on top of the high-density metal. They don't want to mix. It's solid oil and water, and yet a third phase. No separators. So this has gotten some recognition last year. They picked it in the TR10. And the thing is, with that Deshpande Center money and Chisona's Foundation money, I did this with one graduate student. One graduate student, David Bradwell, also born in Toronto. David and me. And these people, these are all UROPs, and they're freshmen. They're not all freshmen now. They do graduate and go on, but at the time, they were all freshmen with one semester of freshman chemistry, and I took them out of 3091, and I got them into my lab. And they're all the top students out of 3091. You know why? Because the top students want to work on this problem, because they want careers with meaning, and they see this as an important challenge. Said, it can't be done. They said, I'm there. That's what I love about MIT students. And we now have some sponsorship from off-campus, including a big ARPA-E grant, some money from Total, some DARPA work, of course, MIT Energy Initiative, and some support from Mass Clean Energy Center, and a grant. We have not started a company. This is not venture capital funding. They gave us money. They said, this is an important problem. Here's $100,000. And I said, boy, I'm glad I answered the phone. So I hope I've shown you that electrochemistry and energy storage are the most critical problems, and this is the most critical discipline. You know, Ernest Rutherford said that all of science can be parsed into physics and stamp collecting. He was close. It's really electrochemistry and stamp collecting. And I like to show this slide because in the old days, before the euro came into being, we see Alessandro Volta and the very first battery on a unit of currency of a national government. Volta was a professor. He was a professor at the University of Padua. He invented the battery. He changed the world in two ways. One is he gave birth to the power source. Right? Gave birth to the power source. And in doing so, he reversed the paradigm. It's arguable that until Volta, every advance in material science came first from the artisan, from the craftsman. People knew how to glaze pottery long before a professor could give a mediocre lecture on the structure of silicate melts. And people knew how to build swords and horseshoes long before a professor could give a mediocre lecture on the phase transformations in iron. But Volta changed that. Volta invented the battery at the university first, and from there disseminated technology, electrowinning, electroplating, electroforming. Volta, by doing so, demonstrated the utility of the professor. That's correct. The second thing he did was gave birth to the model of sponsored research on campus. Because people figured, you mean a professor is capable of inventing something useful? Let's see what he could do if he were funded. Well, back in those days, of course, they were all noblemen and so on. All right, so I made a comment about 3091. So I want to take the last few minutes here and talk about, and I'm watching the clock, talk about innovation and thinking differently and against the grain in teaching. And teaching in a venue where people say you can't innovate. Big freshman class, 500 students. Oh, sure, studio physics, that's great. You got groups of people sitting around high-tech table and so on. Put this number of people in a room, one human being with a piece of chalk, go. Because that's the cost model. You cannot afford to put 500 people around desks of 9. You've got to get that basic material out there somehow. So what are you going to do? Well, I'm going to tell you, everything I needed to know I learned here. I learned by teaching. See, I didn't know chemistry till I came here and was asked to teach chemistry. That's a secret. So you satisfy the chemistry requirement either through course 5 or through course 3. And the big difference is that in course 5, the focus is the molecule, whereas course 3, the focus is aggregates of molecules or solids, because engineering systems are made of solids. And I don't just mean the solid that powers this laser pointer. We are solid state devices. This is soft matter. My eyes are photodetectors, band gap of about 2 electron volts. They're just not made of a compound semiconductor, inorganic. And this motion is just conformational changes in a polymer. See, it's all chemistry. The rest is stamp collecting. So what's 3091? Why does it exist? Because it certainly doesn't have the brand. Lays the foundation for more chemistry because our undergraduates come here with no bias. They're free to choose anything they want in the freshman year. We can't tell them choose anything you want, and then when they choose their major in the second year, say, oh, you made a mistake when you chose your chemistry. It has to be open. Prepare students for their majors, whatever their majors will be, and I'd like to think that we provide scientific and technical literacy beyond. There was a dean of engineering by the name of Gordon Brown, who said that the mark of a great education is that it is redeemable at par 25 years out. You don't just finish and the next thing you know, you're in a continuing education class. Doesn't that it's kind of crazy, isn't it? I just finished and I got to go to school. What's this degree worth? So the other thing is, you know, most people don't want to take chemistry. The students who come here love math. Physics is good. Biology, fascinating. Chemistry, is there a way that we can avoid chemistry? I love the challenge. I want to take that group of hostiles and make them say at the end of the semester, that was my favorite class. So we use the solid state to teach engineering applications and illustrate principles of chemistry. But this, you would expect that. You say, oh, he's an engineer, so he's going to give them some examples. But this is different. Integrates subject matter from beyond chemistry. Not physics, not math. I take that for granted. Art, literature, music. See, it's not a chemistry class for me. It's chemistry-centered class. So this is thinking against the grain. If this is the universe of subject matter that we would say belongs in a general chemistry class, and this is how much you can sensibly cover in one semester, even at MIT, you have to make choices. And the difference between the two subjects is 511.1 and 511.2 go here, 309.1 goes here, and there's sufficient overlap, which I would argue is about 1/3, that allows students to choose either or any one of the three without penalty. And what's in there? That's the electronic structure and its relationship to bonding. And then after that, they go in their direction. I talk about solids. So this is the classical view. Electronic structure informs bonding, but then in 309.1, bonding informs atomic arrangement, which tells you everything. The shape of all things. It's all electronic structure. There's nothing more. So let's take a look. I'm going to take you into the class, and it'll be a little bit lighter. No more slides of yet another data point, okay? Just trying to make you happy before you go to lunch. So the concepts illustrated by examples. It's a 15-minute period, as you know. I lecture for 45, and then the last 5 minutes, I use some example from what I broadly call chemistry in the world around us. Reference to music, art, film, and literature, not just there, but in the body of the lecture. And also I want to show them that laws don't just appear on the textbook page. Real people living in real places at real times gave birth to these guys. I'm fascinated with why did all of these discoveries take place in this place at this time and not someplace else? Because that'll get students thinking. Because they're smart. They can memorize these formulas. In fact, I let them take the exams with an aid sheet. I don't care, because there's only one thing that happens to your memory over time. It gets worse. So, actually, I don't hear anything, so I don't know whether we're getting any sound or not. So the way that started the chemistry and music, I was the summer that I first started thinking about taking over 309.1, I was going to teach it in the fall of '95 for the first time. I said, on the day I teach hydrogen bonding, I'll play a little bit of Handel's water music. And I thought, why should I play music only on that day? Why don't I play music every day? But I can't just play music because the professor likes music, although that's true, and although I am the professor, and therefore I could do almost anything in that class. But that would be an abuse of power, and that wouldn't be me. So there has to be thematically linked. You see, the band theory came about in the late 20s and early 30s, but it was popularized in the 40s, which everybody knows is the big band era. That was a joke, and I know you're hungry. Moseley was the one who first figured out that Mendeleev was close but not right. In point of fact, Mendeleev said that the periodic table is arranged in ascending order of atomic mass, and there are 4 pairs of elements that's backwards. By the way, potassium is less massive than argon, but nobody would put potassium under neon. And it was Moseley that figured out that it's something else, it's the proton number, and he coined the phrase atomic number, but he enlisted in World War I at the age of 27 and was killed at the Battle of Gallipoli. And so I play something really. Central Europe and quantum mechanics.
Catch a wave and you're sitting on top of the...
We have a lot of students from California, so and if you're talking about wave mechanics, I guess that works. Anybody guess this one? One of the people living in Moscow at the same time as Mendeleev was, see, I'm drawing a blank here, having a scene. Borodin. Do you know what Borodin did for a living? He was a professor of chemistry. Seriously. And he wrote, among other things, the Pavlovian Dances, Prince Igor, and so on. So that's kind of nice. Superman has X-ray vision, yes. Except the comics are wrong. You know, if I want to irradiate something by X-rays, I have an X-ray source, and then I have a detector. Superman shoots down, right? If you've seen him in the comics, he does this, and somehow he sees. So. Quasi-crystals, five-fold symmetry. So we need songs with 5/4 times. Polymers, chain of fools. For DNA, that's a twist. You know, you've heard people use the term, the chemistry between people. I always thought that was sort of a 60s term. It goes back at least one generation. Now, I'll play you a little clip from Guys and Dolls, which was Dashiell Hammett, 1951.
Would you like to hear how a gambler feels about the big heart throb?
No.
Well, I'll tell you. Mine will come as a surprise to me. Mine I leave to chance and chemistry.
Chemistry?
Yeah, chemistry. Suddenly I'll know.
Okay, then it gets really, yeah. All right, when we teach X-rays, I bring in some art. So this one here is The Angelus. The Angelus by Millet was painted for a Boston insurance company. The Boston Brahmins loved Millet and his portrayal of life in rural 19th century France. Salvador Dali had to paint this as part of his art education. He hated this painting. It spooked him. And so in 1963, Dali, at the height of his career, asked the curator of the Louvre if she would have this X-rayed. And they X-rayed it, and they found that here, the painting had been painted over. It wasn't an art forgery. It was Millet himself that had painted it over, and guess what they found underneath? This is not a painting of two people giving thanks to God for this pitiful bounty of potatoes. They are grieving over the loss of their child. This is the casket of a baby. Well, this is how to get X-rays and to integrate the art and so on. It's very good. All right, and so I've seen this pose. I was in Rome at the Galleria Borghese, and I saw this one. And then ultimately, Dali took his revenge, and he showed this. See, the woman is taller than the man. You see where the man's got his hat, and this is Dali and his father. There's all kinds of things that I'm not going to bother talking about before lunch. But you can see the imagery here. And this I'm showing them in class, and they're looking at all of this. And then since I've got them going on Dali, I show them the hallucinogenic Toreador, which Dali painted after going out for a walk in Manhattan to buy a box of Venus pencils. So all of this is trompe d'oeil with Venuses. You see? You see the face of the Toreador? The tam, there's his cape. Huh? Oh, yeah. So let's look at the life force coming out of the bull. There's a symmetry plane. All of these Venuses look forward. All of these look back. We've already studied crystallography, so they can appreciate this. There's the crystal structure of the life force leaving the bull, another symmetry plane. See here, symmetry, symmetry. You see that in art, get them looking at it. This is another one by Dali. This is DNA. It's a very poor image here, but this is DNA, and he's basically saying now that we have determined the scientific basis for reproduction, we still haven't figured out how to stop killing ourselves. All right, but look at how the human forms are arranged. These are in cubes, cubic arrays. And in fact, this is simple cubic. I joke that if we put a fifth body right here, it would be body-centered cubic. That's a material science joke. Obviously, not many course 3 majors here. We bring in the Michael Frayn play Copenhagen in the class and talk about the morality of what happens when people are trying to decide whether to develop nuclear weapons. So this has 3 people. There's Niels Bohr. This is Werner Heisenberg, his former student, who is now the head of the Nazi equivalent of the Manhattan Project, who comes to see Bohr in 1941. And there's Margaret, Bohr's wife. So you can see they're arranged like a one-electron atom. Bohr is the nucleus. Heisenberg is moving around, and Heisenberg gave us the uncertainty principle, and Margaret is the observer. And it's a beautiful play, and people read it after going to the lecture. There's actually a BBC production of this with Stephen Ray playing Niels Bohr, Francesca Annis playing Margaret Bohr, and who is playing Werner Heisenberg? That's a young Daniel Craig, and he does a convincing Heisenberg. This is one of the most boring topics that I have to lecture on. Taxonomy of defects. You might say, why is he doing this? If I gave you the chemical origins of reactivity, you'd say, yeah, that makes sense, that's chemistry. Here we're talking about the chemical origins of mechanical behavior. The chemical origins of mechanical behavior. So we talk about bonding, we talk about perfection in solids, and then we talk about imperfections. And just as with human behavior, the most interesting qualities are found in the imperfections. So here's the various defects, and at some point we get to the example of so this is a rivet from the Titanic. This is Tim Fecky at NIST. And one of the defects that we talk about is volumetric defects. In this case, we have slag inclusions. And so what we see here is oh, shut up. So what we see here is the slag inclusions that ultimately took the Titanic down. And it's really a story of human greed. It's really a story of human greed. This is how they made steel back in 1910. And this plant was in Ireland, which was still part of the United Kingdom at the time. The Titanic was built in Belfast, which was a part of the UK. So you have these two, imagine something about the size of this stage and one flame coming in here and another flame coming in here like two dragons. And I've got metal up to about my waist for 12 hours waiting for the slag to separate from the metal. But if I get greedy and I pour the heat before everything's separated, I've got bits of slag down in here. And then when we roll the rivets, it's like a perforation on a sheet of postage stamps. And so when the vessel hit the iceberg, instead of just opening up at that one place and taking on water over the period of a day or so, all those rivets just broke. They were as brittle as glass. She keeps coming back. This is five-fold symmetry. This is an exciting piece of research that I bring into the classroom. This was done at NIST, where Danny Shechtman, who was on sabbatical from the Technion in Israel, was studying some X-ray diffraction patterns, and he found five-fold symmetry, which violates the laws of crystallography. It should not have, you can have five-fold rotation, but it doesn't have translational symmetry. It's the atomic equivalent of Penrose tile. All right? Now, this is Danny Shechtman's lab notebook. So imagine we're looking over his shoulder, and look, April 8th, 1982, it's 25% manganese and aluminum, and he can't believe that he's getting what he's writing as tenfold symmetry in his X-ray diffraction pattern. So we're all looking down over his shoulder. You need something with five-fold symmetry, so it's a 5-4 thing, mission impossible. We talk about historic development of science, people, and times. One of the themes I have is women in science, which I subtitle Studies of Abuse. And I do this so that people understand the history of the discipline. So early in the class, we talk about Cecilia Payne, who was the first person to recognize that the sun is made of hydrogen and was forced at Harvard to put a recantation in her thesis saying, most assuredly, this finding cannot be right. Lisa Meitner, who was looking at Otto Hahn's data of the twinning of the nucleus and said, look, I think what you've got is splitting here, and she coined the term fission, rather, and of course is not on the Nobel Prize in 1944. And of course, Rosalind Franklin, for her work on the X-ray crystallography of DNA, and you've got 1, 2, 3, 4, missing space 5, which is the signature of the double helix, and how that piece of information was used by Watkins and Crick. We also try to get them to go to primary sources. So when I teach the Bohr model of the atom, I start with the first page of Bohr's paper, and I read from it, and get them to go to primary sources. Here's the paper by Watson and Crick. This is the first published image of the double helix. So they have to go to this, and there's Rosalind Franklin, a better definition of her pioneering work. This is a Sadoway backscatter. So they can look at this and say, oh yeah. We also have some fun. So I make them at some point early in the semester write down the periodic table from memory. And as people go, what is this? This is 19th century rote learning. I said, no, everybody should know, if they're educated, that cesium lies under sodium. I don't ask them to do the lanthanides and the actinides, okay? But they have to do the upper block. S, P, and D block elements, they have 10 minutes and a blank periodic table. They're done in 3 minutes, and then they're very proud. All right, so we have a contest for lanthanides to get the 14 lanthanide elements and the 14 actinide elements. And, they come up with stuff like lazy college professors never produce sufficiently educated graduates to da-da-da-da, But once in a while, you're surprised. Once in a while, you're surprised. So this one came to me one year. Blake Stacy recognized there's 14 F shell electrons, and there's 14 lines in an Elizabethan sonnet, and so he does a takeoff from Shakespeare's Sonnet 57, where the first 2 letters represent the letters of the elements. 3 stanzas, 4 lines each, with the rhyming couplet, and what nailed it for him was when he used smelting here for samarium, he knew I was a metallurgist, he had me, so that was... Now, this last one really takes the cake, all right? I don't have to say too much. So this was Jordan Stone, and I'll just let it go here.
Let's start from the very beginning, a very good place to start.
I won't play the whole thing, but she goes through the whole periodic table.
With A, B, C, and the first 2 elements happen to be H, H, E, H, H, E. The first 2 elements happen to be H, H, E, H, H, E, H, H, E, L, I, V, E. By increasing atomic number. H, H, E, L, I, B, E, B, C, N, O, F, N, E, N, A, M, G, A, L, S, I, P, S, C, L, A, R, K, C, A, S, C, T.
Okay, you get the idea. There's lots more, but the time won't permit. So I'm gonna start winding it down. So I want to just remind us of what's this all about. It's not about just entertainment. It's about engagement and getting students invested in their learning. And I hope I've given you a sense of how they do so. But ultimately, I'm still trying to teach them the rudiments of chemistry and give them lessons that there'll be a high retention factor. So what is education? I don't know. Here's one definition. I'm not even sure Franklin said that. But it's being prepared for a problem that you've never seen before, isn't it? Or another way to think about it is I tell them on the last day that, the chemistry class has at some level been part of the transition. I'm trying to take them from student to scholar, to take ownership of their own learning. And you got to do that by, these young people, they want to be told. You've got to induce them. And so a good education teaches solutions to problems. Back in the 30s, you went through the chemical engineer's handbook, the mechanical engineer's handbook, and if you ever met that problem again, you knew the solution. Well, an MIT education is way better because it's an analytical education. It teaches you the methodology for developing solutions to problems. So you've got the framework, the mathematical framework, and the way to think. And that's good, but I'm not satisfied with that. I want to go to a higher level. And the higher level is a great education, which is the methodology for developing methodologies. So in the end, it's all just archetype on top of archetype on top of archetype, and chemistry happens to be the test vehicle. Solid state was the test vehicle for teaching chemistry, and chemistry was the test vehicle for teaching, learning, and ultimately innovation and invention. So I want to use the words of somebody else, and I love these words because I was in 10250 the day that President Hockfield was first revealed to the community as the new president-designate. I want to be the dream. I love the term dream. You know, dreams power us, and you know, they're like stars. You can't touch them, but they allow us to, they give us direction. So I want to be the dream of every child who makes the world a better place. And this is a big departure. You know, it's not just cool technology. It's technology. What kind of technology? Technology in service to humanity. Okay? Hotbed of innovation, service to humanity. That was August 24th, 2004. And, you know, many people in this room will recognize this quote. Some men see things as they are and ask why. Others dream things that never were and ask why not. And that's an MIT culture, isn't it? Only it's technology-centered. So how to go against the grain, how to inspire people to think differently, and you got to bring them along. So what's my model for education? How do I try to do it, both in my research and in my teaching? I go back to simplicity. Simplicity gives transparency, gives clarity. So it's back to Rutherford and Bohr, you know, the simple one-electron model of the atom, the nuclear model of the atom. Question is, what's here in the nucleus? Is it the professor? Is it the department? Is it the university? Is it the alumni association? What goes here in the center? And my experience is, when I put the student at the center, chances are 99 times out of 100, I'll make the right choice. Now, having said that, I will assign myself the position of the 1s electron. So I'm going to bring this to a close by saying I hope that I've given you some glimpse into how I go about thinking differently, going against the grain. I never knew there was a grain, so I guess that's in my nature. All right, thank you.
We have some questions.
I'm not answering any questions. I'm kidding. No, okay, I'll take a question.
How do you maintain metals in a liquid state in a battery? Please answer in iambic pentameter and sing.
You haven't heard me sing. Okay, so I'll start with a dacty or a spondyle, and then we'll go into the hexameter. So look, this operates at elevated temperatures. There are very few metals that are liquid at room temperature, but we don't have to be at room temperature. The battery stays at temperature by the current flowing between the electrodes, and it takes a small amount of current to keep it at temperature. And so it's, you know from working with your laptops, when you discharge your laptop, it's warm. When you charge your laptop, it's warm. It doesn't matter which direction the current goes, the Joule heating effect is there. So it's the Joule heating effect. It requires a jump start to get it going, and then after that it runs. And usually the B part of the question is what happens if you're without power for an extended period of time. These things will sit at temperature for days. So, it's okay.
What about using phase changes to release energy?
You can use phase changes. People use them for maintaining temperature in buildings. There's a whole set of efforts that involve tailoring the solid-liquid transformation temperature of salts so that you peg it, say, at, I'll pick a number, 75 degrees Fahrenheit, and so when the sun beats down, the enthalpy of fusion is taken to melt the salt and keeps the interior of the building at temperature. And then at night, if the temperature drops, gets cold, then the salts freeze and they give off their enthalpy of solidification, and that keeps the place warm. But here we want electric current. We want electric current. Remember, you know, as Anand told us, it's electrons in motion. That's what keeps the world moving. It's electrons in motion.
Is this going to be feasible with residential size units?
Great question. That's the funding that we have from Total is to develop a 30 kilowatt hour unit that's about the size of a small refrigerator. Imagine this downstairs next to your water heater and your furnace, and it could take you off the grid. Yeah. Yes.
What are the next challenges, in your opinion, in solid-state chemistry?
In solid-state chemistry? Oh, I mean, Anant gave us some good examples. Energy conversion, sensors. I think the fusion of solid-state chemistry with life sciences, I think that's a very exciting frontier.
And a last question. At this point, can you estimate the cost per kilowatt hour and energy density of a production product? And I mean, I guess a related one to that is, would it help if we boosted the cost of burning hydrocarbons in some fashion to adjust the cost per
No, I think I want to step up to the real challenge. If carbon taxes come, it'll certainly accelerate what we're doing. But I think that we want to stand up to the measure of the marketplace. And right now we're looking at units that are priced using current pricing at current volumes, somewhere in the vicinity of about $300 a kilowatt hour. And there's one chemistry that we're looking at that would get us down to $50 a kilowatt hour. The energy density is about 100 watt hours a kilogram, 125 watt hours a kilogram, which is roughly lithium ion. But that's not the issue here. People have been distracted by saying, gee, if we just had more powerful batteries, not for stationary. The problem is not energy density, it's cost. You see, in a cell phone, in a laptop computer, there is no competition. After 9/11, the thought of having a fuel cell-powered laptop is forever gone. So you cannot use hydrocarbons in those portable electronics. But where you can use hydrocarbons, then you have to face the cost of hydrocarbons, and hydrocarbons are enormously powerful. That's why we use them. Liquid fuel is fantastic. But the liquid fuel is used once. So even though gasoline is 12,000 watt hours a kilogram and the battery is 100 watt hours per kilogram, forgive me, I can use the battery 10,000 times. And I can generate power carbon-free, which you can't do axiomatically. You can't generate carbon and burn it carbon-free. If it weren't for our concern about carbon, none of this makes sense.
Thank you very much.